Hello and welcome to part 2 of the homework 1 vectorization homework for computation methods. So in part 1 we created a function that could calculate the Jacobian of a curve that is defined by these following parameters in x, y, and z directions here. So we used that and we compared it to the automatic Jacobian differentiation through JAX and found that they were the same. So in part 2, we're going to calculate the Frenet-Serret tangent and normal vectors for this curve, and then also talk about how you can find the radius curvature based on these equations. So first and foremost, we have to talk about what the Frenet-Serret is. So let's look at Wikipedia, because the images and drawings on Wikipedia seem to be able to make the whole concept easier. So, as Wikipedia says, the Frenet-Serret formulas describe a particle's motion through three-dimensional space. So, specifically, they describe the derivatives of the tangent, normal, and binomial unit vectors. So the tangent, normal, and binomial unit vectors are three vectors of motion that you can use to define the motion of a particle at a very specific point. So the tangent is a point pointing in the direction of motion of the particle. Then the normal points towards the center, which is perpendicular to the tangent. And the binomial is the cross product of the tangent normal. So by definition, it's perpendicular to them both. And these are the formulas here. So the derivative of the tangent with respect to s is the normal times the curvature of the curve. And then these are the other two, where the curvature shows how the curve is moving, how different the curve is from a straight line. And the torsion shows how non-planar it is as it rises or falls as the curve goes. So now what we're going to do is we're going to actually calculate these three vectors, which these are the three vectors here, and you can see as it's moving along the curve, you can see how the vectors are moving or changing. So the way you calculate these is the tangent is defined as the derivative of the curve itself. So r is the curve, derivative of the curve, over the change in its arc length. So that immediately poses a problem for us, because our curve, defined by here, is we don't really have a good way of finding the arc length directly, because ours is parameterized in terms of, well, we got the curve, we also have t. So what we have to do is we have to figure out a way around this particular problem. And the way we're going to do that is we're actually going to use the chain rule, and we're going to use this guy here. So this here, it gives you a relationship between the curve and between the arc length. So what we're going to do is we're actually going to take the derivative of both sides with respect to time. So we'll get the change in arc length over time is equal to the norm of the curve. And norm is a linear algebra term, or a linear algebra function that we'll be able to use through NumPy. All right, so then knowing ds dt, we're also going to take dr dt, so calculate the derivative of the curve itself with respect to time. And then by dividing one by the other, we can use chain rule here to cancel out the dt's, cancel out the time, and then get our equation in terms of the curve in terms of arc length. So let's go ahead and get started. So first and foremost, we're going to block off what we did last. Name this section Frenet-Serret. Then we're going to hide those so that they're out of our way. Then we're going to define our F. We're going to define our Frenet-Serret. And we give it a function. So first thing we need is we're going to need to calculate this ds dt. Okay? So ds dt and our ds dt is simply equal to take derivatives of both sides of this here. And ds dt over, remember, taking the derivative will cancel this, and we'll be left with the norm of our function. So ds dt equals np dot now dot norm of our function. Now we have that. Then what we're going to need is we're going to need, oh, excuse me, I just noticed that this is actually our prime. So this is actually going to be df dt, isn't it? Which means we should probably define what df dt is. So df dt equal to, and we're going to use our Jacobian, Jacobian. We're going to use the Jacobian that we talked about in part 1, except we're going to use Jax's automatic differentiation of f. Then we're going to solve this at t. Okay. So that's going to give us our ds dt and df dt. So now that we have df dt and ds dt, we're going to use this chain rule here by dividing df dt, dividing it by ds dt, so that the dt's cancel, and we're left with df over ds to get our tangent. So let's make this another one. Tangent t. And we're going to return. I should probably return that too. We want our tangent to equal df dt t divided by ds dt t. And we'll return our tangents. Okay. So now that we have our tangent, we want to also find this normal, right? So our normal is defined as the derivative of tangent with respect to s, with respect to arc length, divided by the norm of that derivative. So let's first calculate our dt over dt. And to get that, we're going to use, well, we're going to use Jax, right? So Jacobian of we don't need that. All right, so we have our dt, and then we're going to use the same trick we pulled to calculate the tangent to then get this derivative tangent over arc length. Then we're going to need, let's just make it variable v, and that's going to equal dt divided by our ds dt. That's both of those a t. Oops, what was that? Then we're going to do our normal is equal to, and now remember, our normal is equal to this divided by its norm. So we said v, so we set this equal to v, so v divided by np dot, norm of v. Okay. Then we're going to return normal. Then for the overall function, we're going to return tangent and normal. Okay. So let's just give it these extra spaces. Run that again. All right, so now that we've built this function that can give us both the tangent and normal vectors, then we want to, okay, then we're going to explain how it can be, so now we've created this function, then we're going to, well, the way you can calculate for the curvature is by doing this guy right here. And we already looked at doing the derivative with respect to time, and that can help you also calculate the curvature, and you can actually work backwards from that point. So let's just make sure our function works. So tangent and normal equal f underscore s, and we're going to actually copy this over. Close that. Copy that. And run it. Okay, no errors. So in the next part, we're going to actually work with that a little bit more to kind of build more into it, and then look at looking at the actual surface vectors. So join me in part 3.